Okay, in this video I'm going to do several examples from the textbook that illustrate essentially all of Chapter 8. So Chapter 8 was sections 8.1, 8.2, and 8.3, and they're all pretty much about this thing called the sampling distribution of the sample proportion. So I'm going to do 3 examples that kind of illustrate what kind of problems can come from this section and basically just how to do those types of problems. All right, so first off, here's an example. Let's say a case study of 46 males with pierced tongues found that 27 of them essentially had receding gums, which can lead to tooth loss. So there's 46 males in my sample, essentially. They all have pierced tongues, and they found that 27 of those 46 had receding gums. So this is the sample, right? And we want to use this information to say something about a larger proportion of males, a larger population of males with pierced tongues. So suppose we are interested in learning about the value of P, which would be that proportion of all males, right? So P is a population parameter, and in this scenario, it would be the proportion of all males with pierced tongues. That's my population of interest. So this is my population. So that's what makes it a parameter. And I don't know what P is, right? It's unknown. But we want to look at the proportion of those people in a population who have receding gums. So this proportion from the sample can be used as an estimate of that unknown P. So what is the value of P hat for this sample? Well, P hat, it's literally defined as, right, the sample proportion of males with pierced tongues. That have receding gums. So I take, essentially it's just the frequency, right, 27 over 46. And my sample proportion then would be 0.587. So you can say 58.7%, right, of our sample had receding gums. So this P hat essentially is our best estimate for this unknown population proportion P. And right, so we want to know every sample would have yielded something different. So what is the error in this? So we could ask, is it reasonable to think that this estimate is within 0.05 or 5%, right, of the actual value of the population proportion? Well, the standard error is essentially the standard deviation of the sampling distribution, which is defined as the square root of P times 1 minus P over N. But this thing, we don't know what P is, so we can get a handle on what the error is by substituting that in with P hat. So to calculate the error, I would take the square root of 0.587 times 1 minus 0.587, all over the sample size, which was 46. So this gives me essentially the error in this estimate. So put this in your calculator, we would get, let's see, 0.587 times 1 minus 0.587 divided by 46. 0.0726. I'll just write 0.073. So the error is about, right, 7.3% on either side. So no, it would not be reasonable. You see what I'm saying? So my error is actually pretty big. It's bigger than 5%. It would not be reasonable to think that this estimate is within 5% of the true population proportion. Okay, so that's kind of how you determine a point estimate, right? So this is called a point estimate with its associated error. Okay, so let's look at another example. Say we have, suppose that 20% of the customers of a cable television company watch the shopping channel at least once a week. And this was true back in 2010. So back in 2010, this company knew, they looked at all of their customers, right, up until that point, and they said 20% of the customers watch this channel at least once a week. So now the company plans to take a random sample of 100 newer customers, maybe between 2010 and 2020, right, to check to see if this percentage has changed or not. So before the company takes a sample of 100 customers to find P hat, right, that would be my sample proportion of those 100 customers, is the distribution of all P hats from samples of this size normally distributed. So before we even do any inference, we have to kind of determine if it's normal or not. So here n is 100, and p, right, we're going to assume that p hasn't changed, correct? So p is still 0.20 or 20%. So I do these two quick calculations, right? N times p and n times 1 minus p. And I get 100 times 0.20, and that would be 20. And I get 100 times 0.80, because that would be 1 minus 0.20, and I get 80. Both of these things are bigger than 10. So yes, it is normally distributed. Okay? Now, the central limit theorem says that not only is it normally distributed, but the mean of all possible p hats is equal to p, which would be 0.20. And the standard deviation, which is similar to the previous problem, right? It's the square root of p times 1 minus p all over n. And in this case, we are assuming we do know p, correct? We're taking 20% as that's what it used to be, and now we're going to say that's kind of the status quo, right? That's what it still is, and we'll determine, right, later when we do a sample if it has changed. So here we get the square root of 0.20 times 0.80 all over 100. So if you put that in the calculator, I would do the square root of 0.2 times 0.8 divided by 100, all within the square root, and I get 0.04. Okay, so that's my standard deviation, and this is the mean. Now I can answer a lot of different questions, right? What is the probability that the sample produces a sample proportion greater than 25%? So with this information up here, before the company even samples these 100 people, they can actually find the probability that it would be bigger than 25%. So what does that mean? Well, what we have here is a sampling distribution, I don't know why I drew it over here, between 0 and 1, and the mean is at 0.20. So what we have is a normal curve, right? Because we already determined that it's normal, centered over 0.20. What we want to know is, right, what's the probability that my p hat that I get from the sample is greater than 25% or greater than 0.25? Well, 0.25 is to the right, right, of 0.20. So what I'm really looking for is the area, correct? The area to the right of 0.25 on this little curve. Correct? So we can already see that, right, what is one standard deviation? 4%. So this is just a little bit above one standard deviation to the right. So the probability is probably not that great. But let's find it out anyway. I change the z-scores. I do 0.25 minus 0.20 over the standard deviation, 0.04. So I'm essentially finding the z-score. So here I do the probability that z is greater than, so what would be 0.25 minus 0.20? That's 0.05. Divide that thing by 0.04. I get 1.25. Yep, that's what I thought. So it's 1 1/4 standard deviations above the mean. So to find this probability, I have to do 1 minus the z probability that the z value is less than 0.25, because in table 2, this is the value that I give. I don't get the ones greater. So I look this up in table 2. I get 1.25 is 0.8944. Subtract that from 1, and I get 0.1056. So we can interpret this to mean, right, there is a 10.56% chance the sample of 100 customers yields more than 25 that watch the shopping channel. At least greater than or equal to once a week. Okay. So why did I say more than 25? Well, 25% of 100 is 25. So 25 of the customers or more watch the shopping channel at least once a week. So there's a 10.56% chance that'll happen. Okay, another thing we can do is something like this. So let's say an article reported that 56% of 600 social network users surveyed indicated that they thought it was not okay for someone to friend his or her boss. Okay. Suppose that this sample can be regarded as a random sample of social network users. Is it reasonable to conclude that more than half of social network users feel this way? So here, 56% is my sample proportion. So the information about the sample is, right? P hat is 0.56, and the sample size was 600. Now, in this scenario, suppose that this sample can be regarded as a random sample. Okay, so that's fine. But we want to know, is it reasonable to conclude that more than half of social network users feel this way? So our p hat says that, yeah, right, we got more than half, but maybe that was just random, correct? Maybe it was just kind of a fluke that we got 56%, and we could have gotten 47% otherwise. So what we do is we assume, right, that p, the true proportion, is 0.50, and determine, right, the probability that p hat was at least as great as 0.56 on the sampling distribution. Okay, so assume, right, here's our assumption. We're going to assume that p is 0.50. Then what we need to do is check to see if the sampling distribution will be normal. Well, I would take 600 times 0.50, 600 times 1 minus 0.50. And what do we get there? Well, I think everyone can see that we'll get 300 in both cases. So yes, it is normal, right? In fact, what would be, under this assumption, what would be the mean? Well, that's just equal to p. And the standard deviation under this assumption would be the square root of p times 1 minus p over n. So that would be the square root of 0.50 times 0.50 over 600. And right there, what do we get? The square root of 0.5 times 0.5 divided by 600 gives me 0.02. So there's only a 2% variation in this thing. So right away we can see that if we were assuming 50% of the population, right, thought this was not okay, then my standard deviation is 2%. And so getting 56% out of a sample of 600, that's 3 standard deviations away. So it's very rare that I would have gotten this. So that gives me more evidence that it is reasonable to conclude that it's more than half of social networkers, because getting 56% was so rare of an event. How rare? Well, it was 3 standard deviations away of my assumed value of p. So this assumption must not be very good. It must actually be above 50. So how do we actually figure that out? How do we actually gain more justification for our claim? Well, actually calculate this, this value. So what would be the probability that it's greater than 56? Well, I would take probability that, let me just go down here. So this would be the probability that z is greater than 0.56 minus 0.50, subtracting off the mean, divided by 0.02. So this is, z is greater than, this would be 0.06 over 0.02, that's 3. So this is the probability that z is greater than 3. I'll write 0.00, because that's in the table. I have to do 1 minus, z is less than 0.300. And I look at the table, 3.00 is right here, 0.9987. 1 minus 0.9987, so that would be 0.0013. So here's what we can say, right? Assuming that p equals 0.50, there is a 0.13% chance of conducting a sample of size 600, resulting in a p hat of 0.56 or more. Right? This is so rare of an occurrence that p, right, the true proportion, must be bigger than 0.50. Right? So yes, it is reasonable to conclude that more than half. Why? Let me just recap one more time. But by the way, this is the element of a hypothesis test, which we'll talk about in the coming weeks. But I want to know if it's reasonable to conclude that more than half of social network users feel that it's not okay for someone to friend their boss. Okay, so I went out in the field and I talked to 600 social network users, and I asked them, is it okay for you to friend your boss? 56% of them said no, right? So that's more than 300, right? More than half. Now, was it just a random chance that I got 56%, which is more than half? right? Could it have just been just as likely to get 46%, right? Or something less than 50? Well, how do we determine that? We say, okay, let's test this value of 56 by assuming that the true proportion is 50%, right? I'm going to assume that, right, 50% of people think it's okay and 50% think it's not okay. So if I assume that that is true, I then know the sampling distribution, right, of all the possible p-hats that I could have gotten, right? So under the assumption that it's 50, I know the mean, and I can figure out the standard deviation using the sample size. It's only a 2% standard deviation, correct? With that, I take 56%, I find its z-score under this hypothetical curve, and I find that it's 3 deviations above the mean, which is super rare. So in a sense, it's super rare that I would have gotten 56% out of my sample if this were true. It's so rare of an event that I'm going to throw away my original assumption because there's no way this is true. And so, since 56% landed on the right side of 50, right, the right-hand side, it must be bigger. So the true proportion must be bigger than 50%. Okay, so that all hinges on the fact that this is a very, very rare chance. All right, hope that helps out.